the last time this summer in our Ingenuity 1 series. This is the eighth and final lecture for a while, and I have to say again that we are extremely glad that Professor Stephen Hawking has agreed to come over to the AA. I also welcome Mrs. Hawking, his secretary Laura, and his interpreter Colin Williams. Space-time reality, what a pretentious theme, capable only of being thought of in leaps, to enclose only by simultaneous micro and macro world comprehension, detail and complexity. Understanding that as a human being, one is at the same time directed part and directing part of the universe, one has to be receptive like a child and intellectual like an adult. It still seems to be for our capability of understanding reality very paradoxical. But today, with Stephen Hawking's lecture, we will be closer to reality than in any other of our lectures before. I'll just try to give my interpretation of some basic examples which helped my understanding, hoping that Professor Hawking and Colin will forgive me my unprofessionality, and knowing that by looking at a matter, one already is changing the reality of that matter. This is related to Heisenberg's uncertainty relation, which was for me the first step into space-time reality, and is based on the impossibility to fix time and space at the same time, and means, for example, so I understand that you can't describe simultaneously the movement and the location of something moving. Imagine a ball thrown into the air. One possibility is to see the movement as a film, but you only see the movement of the object. The other possibility is to see it as a photograph, but you only see the location of the object. Whenever you try to describe the location and the movement of that object at the same time, you fail. Because every time you say the ball is at this point in the air, it already has moved further, no matter how precise and quick you are. This is leading to the question whether, for example, so I understand again, light is real or unreal, let's say, whether it consists of particles which are moving or waves in which particles are not fixable. We can understand this with light, but what about stones, for example, so real and heavy? Someone will tell us as architects, where we are used to building buildings stone by stone, steel by steel, concrete by concrete, who will tell us that stones consist of chaotic moving invisible microparticles, all out of control in a way, but to put together in a highly concentrated space, executing an incredible fight, one against the others, against billions, but kept together by a magnetic-like overpower. As another dimension, black holes. And so this Earth, this world, the universe, we as individuals, our brain and all we can think of, all black holes, all phenomena of intense gravity, unreal, are all finally chaotic? Yes, I think in a chaotic order, really. The step to accept this paradox is to understand all as the exception, what is like in order, as part of the way of the main and final order, which may be chaos order, and which means in the end the synthesis, the multi-order mode of all ever possible situations, reactions, aspects brought into a formula, maybe the world formula, which is comparable with something like the brain, the black hole, the most possible intense concentration. And again, I would like to say, if there may be architects who think, I don't have to deal with those questions, think about that. A big room can be very tight when it is boring, because nothing is inspiring, like a long street which is very long when it is boring, or very short when it is interesting. And again, Le Corbusier lived the last 2 years of his life in that small cabin, 1 meter 20 by 2 meter 40. I repeat, 1 meter 20 by 2 meter 40, after having thought a whole universe of architecture. This cabin was situated in a beautiful Mediterranean landscape with a fantastic view over land and sea. He didn't need much space inside the cabin because he had this immense and inspiring space outside his window. And next time you draw 2 straight and parallel lines with a ruler, think about the fact that parallels meet in infinity and are bent, like when you look along straight and endless railway tracks. Or stand in front of a mirror, or better, a flexible mirror, and think about reality or realities. Or think about whether 1 plus 1 is always 2. Is it? We shouldn't say anymore, the earth is round, but here it is straight, just because we don't want to think more dimensionally. When gravity can bend light, our brain bends reality. Because I tried to describe some of it, it already changed its content. It's time to deal with space-time reality. We have someone here to tell us, in reality, at this time, in this space. Please, Stephen Hawking and Colin Williams.
Well, when the Architectural Association invited me to give a lecture, I thought at first they wanted me to talk about the design of buildings for disabled people. And this is something I have very strong views about. Architects tend to forget about access for disabled people. But now that is in British legislation and in the building regulations. However, I was told that what they wanted me to talk about was the dialectic between complexity and detail in time-space reality. Now, I don't really know what that means. So what I'm going to tell you about is some recent work that I've been doing about the origin of complexity in the universe. Can we have the first slide, please? Why does the universe display the complicated structures that it does? Like that shown on the next slide. Can we have the next slide? This is a complex architectural structure. Now, how is it that such structures arise? Now, scientists believe that the universe can be divided into two parts. Can we have the next slide, please? First of all, there are a set of local laws which determine how the universe evolves in time. And secondly, there is a set of boundary conditions which determine the initial configuration of the universe. Now, we believe that the local laws are fairly simple. In a way, this is a bit like looking for your door key under the lamppost. We have the next slide. It may well be that your door keys are not under the lamppost, but if in that case, you're very unlikely to find them. And similarly with the local laws. It may be that the local laws are very complicated, but in that case, we would never find them. However, all our experience so far has indicated that the local laws are relatively simple. We have the next slide, please. However, I should say that they are only relatively simple. For example, let's have a look at the next slide. This is simple. This is a part of the theory of n equals 8 supergravity. Which is a candidate for being the ultimate theory of the universe. And as you can see, it looks pretty complicated. But it really is quite simple. Now, if the local laws are quite simple, then the complexity in the universe must depend on the initial conditions. And I have an example to show you that simple laws can lead to very complicated configurations. Now, this is an example of a computer program called Life. Which was devised by John Conway. Now, in this, you imagine that you have a plane divided into squares. And each square can be either alive or dead. If you look at a square which is alive and count its surrounding neighbours, if it has 2 or 3 neighbours, then it will survive to the next generation. And if you have a square which is dead, but has precisely 3 neighbours, then it will appear alive in the next generation. But any squares with less than 2 neighbours will die of loneliness. And any squares with more than 3 neighbours will die of overcrowding. So let's have a look at this program. Do you have this up? Right, the first configuration consists of this horizontal line of 3 live squares. Now, the rule is that we count the squares immediately surrounding each of these and see how many are alive and how many are dead, and that will determine future configuration. So let's start this off. Okay. So that just oscillates between a horizontal and a vertical barge. Okay. Well, let's now try a line of 5 instead. Okay. That still doesn't seem to be too complicated, but we're applying the same set of simple rules to determine the pattern. So now let's now try 2 lines of 5. This is getting a little more interesting. That particular pattern is known as the pulsar of its final state. Now let's try another simple linear configuration which is a bit irregular. Okay? Good. colour creeps around a bit. So this configuration spreads out below the whole size of the screen. But we're still applying these very simple laws to derive this configuration. So a set of simple laws and a simple initial configuration can give quite complex behavior. Okay. Hey, can we have this off now, please? So that shows that if you get a complex structure, then that must depend on the initial condition. Can we have the next slide, please? The next one, please. Thank you. Now let's take a complex structure like a cell, which is what this is. Now the initial configuration for this is determined, the result of this cell is determined by the initial configuration of the planet Earth. Can we have the next slide, please? Now the planet Earth was the result of an initial configuration of a cloud of gas which formed the solar system. Can we have the next slide, please? The first picture, labelled number 1, shows a cloud of gas. With the sun at the centre. The gas rotates around the sun. And in pictures 2 and 3, it starts to condense into planets. And then in picture 4, we have the solar system as it is today. Okay, so where did this first cloud of gas come from? It came out of the formation of the galaxy. Can we have the next slide, please? Now, the galaxy is like a pancake of gas, which is rotating around the center. But the galaxy is only one of many galaxies. Can we have the next slide, please? Here we have about 1 million of them. Which are the million ones which are the most obvious ones around us. But we believe that there are something like 100,000 million galaxies in the whole universe. So we can ask now, where did the galaxies come from? And the galaxies are all moving away from each other. As the universe expands, so what we believe happened was we started out with a universe that was uniformly filled with gas, which was expanding, but the gas wasn't quite uniform. The density would be slightly higher in some regions than in others. And in the regions in which the density was slightly higher, the force of gravity slowed down the expansion of the gas locally and caused it to contract and form into galaxies. In fact, we have a film sequence to show you this happening. In this film, you start out with a lot of particles of gas, which are distributed almost uniformly but with slight fluctuations in the density. Now, as it expands, gravity causes these fluctuations in density to get bigger. And the particles condense into galaxies. So now could we see the film, please? You shouldn't take too much notice of this. Okay, we're only going to be looking at item number 1. Okay. Here you see the cloud of gas is expanding, but with slight fluctuations in density. And now if you look at, say, a region around here, gravity is winning out in this region and making the local density rather higher. And it's condensing to form galaxies. We'll see sort of the same thing again. The cluster starting just there. Fine. Can you stop the film, please? And can you take it back to the beginning? have the next slide, please? Thank you. So the origin of complexity is contained in these initial boundary conditions. But physicists are very embarrassed to discuss boundary conditions. Especially the initial condition of the universe. They feel that that does not belong to the realm of science, but rather to metaphysics or to religion. Now I'm going to make a proposal which will save them a lot of embarrassment. And have the next slide, please. I'm going to propose that the boundary condition of the universe is that it has no boundary. And what I mean by that is that space-time is finite in size, but without any boundary or edge. It's like the surface of the Earth, but with two more dimensions. The surface of the Earth is finite in area, but it doesn't have any edge. At least that is what people used to tell me. But I wasn't so sure, so I've just made a trip right the way around the world. And it's quite true, there is no edge. In fact, I think the universe is very much like the surface of the Earth, but with two more dimensions. Can we have the next slide, please? Degrees of latitude play the role of time, and degrees of longitude play the role of space. And the universe starts off at a single point at the North Pole, which corresponds to the Big Bang. But as you move down in latitude, the universe expands until it reaches a maximum size at the equator. But after that, as you go further south, the universe begins to get smaller again. And finally, it shrinks down to a single point at the South Pole, which is sometimes called the Big Crunch. However, the North Pole and the South Pole are perfectly regular points of the Earth's surface. And similarly, I believe that the Big Bang and the Big Crunch are perfectly regular points of space-time. Can I have the next slide, please? Now, the fact that they're perfectly ordinary points of space-time implies that the universe must be very smooth and uniform near the Big Bang. So, in other words, the universe must have started out very uniformly. But it cannot be exactly uniform because of what Pascal was talking about in our introduction to the Heisenberg uncertainty principle. We have the next slide, please. The uncertainty principle says that you cannot simultaneously measure precisely the position and velocity of a particle. The more accurately you predict the position, the less accurately you will know the velocity, and vice versa. So that implies that the universe cannot be completely uniform. Because suppose that the particles of the universe were distributed exactly uniformly. That would mean that one would be able to predict their position exactly. But in that case, one could not predict their velocities. So even if the universe was completely uniform at one time, it would not remain completely uniform. And in fact, the uncertainty principle implies that the early universe must have started out with small fluctuations in the density. Could we have the next slide, please? Now, as the universe expands, these fluctuations will grow larger and will condense out into galaxies. So maybe, with our new knowledge, we should see that film again. Could we have the film, please? There you see the universe expanding, and it's almost as uniform as it can be initially, but it can't be completely uniform because of the uncertainty principle. And these small density fluctuations give rise to local clustering and galaxy formation. Okay, that's enough, thank you. Now, when you formed the galaxies, then the gas in the galaxies condenses into stars and planets, like the Earth. And then the planet evolves, playing some sort of gigantic game of life. And after about 3,000 or 4,000 million years, and after 3,000 or 4,000 million years, life becomes complicated enough to create creatures such as architects. And that is the highest form of life. So, can we have our last slide now, please? And I think that says it all. Thank you very much, ladies and gentlemen. Yes. Sure.
Would you ask what his thoughts are on the difference between matter and gravitational force? 90% of the matter is.
I'm not sure whether there is enough matter in the universe to bring about moving light. But what I was telling you doesn't really depend on whether that is true or not. what is the most probable length of time that the universe expands before it begins to recollapse. And you find that the longer it expands, the greater the probability. In fact, the probability distribution is really concentrated at infinity.
And one more question. Does the uncertainty principle apply in distribution at time zero? Is our singularity at time zero?
No, there isn't any singularity in this. It's just like the North Pole. The North Pole is not a singularity of the Earth's surface, but it's a singular point of coordinates. And in a similar way, I do not believe that the Big Bang is a real singularity. It's just the origin of time. I'm asking what happens before the Big Bang. It's a bit like asking for a point on the Earth's surface what lies north of the North Pole.
Professor Hawkins mentioned application of which will speed up the process too. What did you think about the next theory regarding the resonance dimensions to explain
There may be more dimensions to both these observed clouds. It may be that at the present time the other ones are held up very small. But what I'm saying what I've said will apply to that case as well. It's just that you have four dimensions that are large and the rest will be small. But there will still not be any boundary.
Is there any circularity in this principle? Could it happen again?
In a sense, it is circular. keep going down in latitude, you get to the South Pole. And then you start to come back up again. If the universe were to recollapse, and we're not sure yet whether it will or not, and it would recollapse to a state which is very much like this now. And that is what is called the Big Crunch.
With the expansion of the universe, does that imply any acceleration of the expansion? If so, does that change the speed of light itself?
The expansion of the universe is really a bit like blowing up a balloon of popcorn. If you blow up a balloon and you look at the distance between two dots on the surface of the balloon, then they will get increasingly separated with time. And depending on how far you blow it up, that will determine how far apart the dots move away from each other. And in fact, you can calculate how the rate of expansion is related to the density of the universe. Depends on the state that the universe is in. We believe that there was a state in the early universe in which the expansion was very rapid. And this goes under the name of the inflationary phase of the universe. This inflation would be even more than inflation in South America. That is only 1,000% a year. 1,000% and a million, 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 million percent.
How compact the universe at the time of the Big Bang?
It was a single point like the North Pole.
One more question.
I'm sorry, we must be the last question because we have to leave the room because of the other events going on there. So, with that, confusion.
Okay, you use the model of the Earth for the model of the universe. You say there's no edge, but in fact, the fact that it is a surface you're talking about, so it is an edge in itself. There's a condition of, well, we're going to the surface in the Earth, and there's a condition going on. Is there an analogous situation in that of that in the universe?
If you were a two-dimensional animal living on the surface of the Earth, you wouldn't find any edge. You wouldn't know anything about the meaning of up or down. It may be that our universe is embedded in some high number of dimensions, so we cannot perceive it. So we can figure mathematical